of like the solution dimension problems, like
Strongest acid plus strong.
okay.
Right. All of them are the same setup, basically. Well, today we're going to continue with, last time, which was the recording, the Zoom recording. You had a chance to check that out. We left off with percent precipitation. And so today we're going to do another type of calculation, actually a number of other types of calculations that involve KSP. So one is fractional precipitation. In fractional precipitation, what we're trying to do is we're trying to separate ions based on differences in their solubility. Based on the solubility differences. And so take a look at the KSP chart and then see what I might be talking about here. So for example, we might try to separate, let's say I had a mixture of carbonate and hydroxide. And I want to separate the carbonate from the hydroxide. Well, I might be able to do that because if I look, at the KSP for barium carbonate, it's 10 to the minus 9. If I look at the KSP for barium hydroxide, it's 10 to the minus 3. And so there's quite a big difference in the solubility, or at least it appears that there's quite a big difference in the solubility, but it's very tricky because they split up differently. So for example, this one breaks up into 2 ions. And so the solubility would be the square root of this. The square root of it would be about 4.5, 9 divided by 2. Whereas this one splits up into 3, so the solubility would be KSP divided by 4, cube root, and so this would be 10 minus 1. So there is maybe a significant difference in solubilities that we can separate out carbonate from hydroxide or hydroxide from carbonate based on fractional precipitation. We can also do this for cations as well as anions. So there are other anions here. Let's take a look. Something like this. We might try using, let's see, we could probably try to separate out the carbonate from hydroxide using lead. Or we could try to separate carbonate from chromate. If we tried to separate carbonate from chromate, both of these split up into 2 ions. And if we look at it, this one's 7.4 times 10 minus 14, this is 2.8 times 10 minus 13. The solubilities are too close to one another. And so these two would be difficult to separate, carbonate and chromate. It'd be like up here. We go back to barium. It'd be like trying to separate carbonate, is 10 to the minus 9, and sulfate, is 10 to the minus 10. These two are very close in solubility, so if we try to, let's say, add barium, we'll end up probably precipitating both of these out. Our goal is to precipitate out one and leave the other in solution. And so let's take a look at bromide and chloride. If we try to separate bromide and chloride by adding lead, if we look at the solubilities, it's 4 times 10 minus 5 versus 1.6 times 10 minus 5. And so they're both about the same. So if we add lead to a solution that contains both bromide and chloride, both will precipitate out. It'd be difficult. So what we're looking for is a big difference in the solubility between the two species, and that could lead to an effective fractional separation. All right, we can do cations as well. Let's say I had a mixture that contained calcium and barium. So barium and calcium. And so I'm looking for an anion that could separate out calcium and barium. So let's take a look at maybe hydroxide. For example, if I add hydroxide, like barium hydroxide is 5 times 10 minus 3, whereas calcium hydroxide is 5.5 times 10 minus 6. So this is 10 to the minus 3, 10 to the minus 6. Both of these split up the same way, and so we can just go ahead and compare the KSPs, and we see that the calcium hydroxide is a lot less soluble. And so maybe we can precipitate out the calcium and leave the barium in solution. And so let's try to separate out a mixture. In this mixture, it's going to contain calcium ions in solution and barium ions in solution. And so we'll put in nitrate. Nitrate salts are soluble. Nitrates are going to be spectators in this case. And let's say I have 0.100 molar calcium ions and 0.100 molar barium ions beginning with this. What I want to do in this fractional precipitation is I'm going to add hydroxide, but I'm going to add hydroxide very slowly. Problem is, if I add hydroxide as a solution, I'm going to get solution dilution, and solution dilution is going to change these concentrations. I don't want those to change. So what I'm going to add is not hydroxide solution. I'm going to add solid sodium hydroxide. If I add solid sodium hydroxide, the sodiums will be spectators and the hydroxide will. And then we're going to assume is the concentration doesn't change, the volume doesn't change much with the addition of solid sodium hydroxide. Here. Okay, so what's going to happen is, as I increase the hydroxide, the calcium hydroxide is a lot less soluble, so that should precipitate out first. And then I have to continue to increase the hydroxide to precipitate out the barium hydroxide. And so what I'm going to do is I'm going to add a little bit of hydroxide to this. If I add a little bit, I need to go slow because I don't want to both. If I dump in a whole bunch of hydroxide in there, then both will precipitate out. So what I need to do is add a tiny bit of hydroxide in here at a time. So I add a tiny bit of hydroxide, say, to keep it unsaturated in barium and calcium. What it means by unsaturated is that the QSP for barium hydroxide is less than the KSP, and the QSP for calcium hydroxide is less than KSP. So both of these won't precipitate. What I have to do in order to get them to precipitate is have QSP greater than KSP. And then I will get precipitation occur. So the calculation that we do when we have fractional precipitation is this. We calculate the amount of hydroxide required to precipitate out both. And so the hydroxide concentration required for precipitation so it looks like calcium hydroxide is going to be smaller, it's less soluble, so let's go ahead and calculate that one first. So we have calcium hydroxide, solid, goes to calcium 2 plus 2 hydroxide. This will be the KSP equation. The KSP expression is just going to be calcium ion concentration times the hydroxide ion concentration. Okay. Squared. So what I'm going to do is I'm going to solve this for the hydroxide ion concentration. So the hydroxide ion concentration is going to equal the KSP divided by the calcium ion concentration, and then we'll take the square root of that. This is going to be at equilibrium. That is, when we're at equilibrium, it's going to be saturated. So this is what we call saturated solution. That is the max amount of calcium. What we need to do, however, is we need to supersaturate it. And so if I add this much hydroxide, I'm going to get it saturated. I have to exceed that in order for precipitation to occur. And so the hydroxide concentration has to be greater than the KSP, the calcium square root. And so let's go ahead and calculate that. The KSP value for calcium hydroxide is 5.5 times 10 to the minus 6. Going to equal square root of 5.5 times 10 to the minus 6 divided by the calcium ion concentration, which was given at 0.100 molar. And so I'll go 5.5 times 10 to the minus 6 divided by 0.1, and then take the square root of that answer. It gives me 7.4162 times 10 to the minus 3. 7.4162 times 10 to the minus 3. Okay, what this means is this is the max amount of hydroxide. If I exceed this amount, then I'm going to get precipitation occur. And so here, what we're saying is, we're saying that QSP is less. Well, if the QSP is less, then that means the hydroxide ion concentration must be less than 7.4162 times 10 to the minus 3. Because if I'm less than or equal, it could be also equal to this. Less than or equal to this, I'm not going to get any precipitation of calcium ion. This is just given. You know, if I have a solution that can use both of these ions at 0.100. Yeah, it's just given. Now, yeah. I can make this trickier because we'll talk about it in just a second. For the barium hydroxide, it dissociates in the same way. So the KSP is just equal to the same type of equation. We'll get the same type of calculation. The hydroxide at equilibrium, if it's equal to the KSP over the barium in this case, then it's saturated. And so what we have to do is we have to exceed this in order for precipitation to occur. Okay, so let's see what that is. The KSP for barium hydroxide is 5 times 10 to the minus 3. Plug that in here. 5 times 10 to the minus 3 divided by the barium concentration, which was given as 0.100, and we'll take the square root of that. So we go 5 times 10 to the minus 3 divided by 0.1. And then take the square root of that answer. And it comes out to 0.22361, 0.22361 molar hydroxide. So what this says is we need a lot more hydroxide to precipitate out barium than we do calcium, because calcium is a lot less soluble. And so to precipitate out calcium, we need more than 7.4 times 10 minus 3. In order to precipitate out barium, we need 0.22, which is a lot more. And so here, the concentration of hydroxide is still too small to precipitate out either. So in other words, I need to bring the concentration up to this and exceed this in order to start precipitating out the calcium. And so, which one precipitates first? This one precipitates first.
What was saying that one precipitates first because the KSP is more reactive vapor?
Yeah.
Okay.
And so this is, what we're going to do is we're going to increase the concentration. So if we increase the concentration of hydroxide, so let's say the hydroxide now is equal to 7.4162 times 10 to the minus 3 molar. What that means is that this is going to be saturated in terms of hydroxide. but it's going to be saturated in terms of calcium, not saturated in terms of barium. So we write that up here. Saturated with respect to calcium ions, unsaturated with respect to barium ions. So now what we're going to do is we're going to exceed this concentration. So now the concentration of the hydroxide, we want to increase more. So here we're adding hydroxide, so we're going to increase the concentration of hydroxide. If we increase the concentration above this, then calcium hydroxide begins to precipitate. So we'll get some calcium hydroxide precipitating down here, but the barium hydroxide will stay in solution because we have to get the hydroxide concentration quite high to start precipitating out the barium. However, the calcium will start to go down, the hydroxide. We want to continue increasing the hydroxide, which will show the principle. And the more hydroxide, the less calcium, therefore. The more precipitation. So we're increasing the hydroxide, which is going to decrease the calcium, which means more precipitation. It would require an infinite amount of hydroxide to get rid of all the calcium, and we can't add an infinite amount. In fact, we have to stop at some point. And so we're going to continue to increase the hydroxide, continue to decrease the calcium, and increase the precipitation. So we'll generate more precipitate here, but eventually we have to stop. Once the hydroxide concentration reaches 0.22361 molar hydroxide, we have to stop here. Because if we stop here, the solution is saturated in barium hydroxide, but it won't precipitate out yet. Saturated with respect to the barium hydroxide. Therefore, if we continue past this point, what we're going to get is both calcium and barium precipitate. And then we end up with a mixture again. We need to separate out the calcium and leave the barium. And so this is going to be the maximum amount of calcium that we can precipitate. There's going to be a little bit of residual calcium left in solution. Well, most of it, hopefully, is precipitated.
So what we did here was we had the barium hydroxide and calcium hydroxide, right?
Mm-hmm.
And for this example, we wanted to precipitate out as much calcium as possible. So we started to add the hydroxide. Okay. And then once we got to 0.2236 molar of hydroxide, we needed to stop because that's the maximum amount of calcium we'd be able to get from that.
Yeah, this is the maximum amount because if we go beyond this, then we're going to precipitate both, which is going to end up as a mixture again.
Right. Okay.
And it's impossible to get all of it, but did we get out most of it, the calcium? And so let's calculate how much of the calcium to us. And so the calculation we have to do is this. At this point, we need to determine the how much calcium ion remains in solution. And so here, at this point, we're going to calculate the calcium 2+ ion remaining in solution. The amount of calcium 2+ ion remaining in solution is just based on the KSP. It's going to equal the KSP divided by the hydroxide concentration squared at this point. The KSP for calcium hydroxide was 5.5 times 10 to the minus 6. 5.5 times 10 to the minus 6. And the concentration of hydroxide here is this, 0.22361. 0.22361. That's going to give us how much? So 5.5 times 10 to the minus 6 divided by 0.22361. 2.4596 times 10 to the minus 5.
So we don't square that.
Oh, I forgot to square this. We need a square. Divided by 0.22361 again. So I forgot to square that. 1.100 times 10 to the minus 4 molar calcium. So there's going to be some calcium ion that remains. So it's not a perfect separation. But maybe it could be a complete separation. So the next calculation we're going to do is we're going to calculate the percent calcium remaining in solution. The percent calcium that remains in solution is going to be 1.1 times 10 to the minus 4 divided by our initial amount, which is 0.100 times 100%. So I have 1.1 times 10 to the minus 4 left. Originally I had 0.1. And what percentage is that? It's going to be 0.11%. It's going to come out 0.11% calcium remaining at the stopping point. And then we need to calculate the percent calcium precipitated, which is just going to be 100% minus the percent remaining. Which is 99.89. 0%. To round it to, let's say 3 sig figs, we'll get 99.9% precipitation. So what this means is at the time we stop this separation, you precipitate out 99.9% of the calcium. If we precipitate out 99.9% of the calcium, you know what that means? That means it's a complete separation. We only have 0.1% of the calcium left. So we got the calcium out of there for the most part. We get the calcium out of there, but what remains is barium. The barium is going to be contaminated with the residual 0.1% calcium. And so this got the calcium out of the solution cleanly, but the barium is going to be contaminated a little bit. But that's okay. We're only interested in the calcium. So this is called a fractional precipitation. And this was a successful fractional precipitation because the success is dictated by how much you get rid of one species and leave the others behind. What's that? Why only calcium? Because if we get both calcium and barium, then we have the same problem. We have a mixture. But now we have pure calcium. There's no barium mixed in it. Well, just whichever ion is okay. Let's take a look.
An example of two different like solutions pretty much, and we wanted to just take one of the ions out. So like it was just an example. It wasn't like we just look at two and just know which one to take out. The problem will ask you, or will tell you which one they want you to take out. That's our example.
Yeah, right. Like for example here. Let's say I had a mixture of bromide and chloride. If I have a mixture of bromide and chloride, I could use silver to separate those out. If there's a difference in their solubilities. And there is a difference. If you look at this, it's 10 minus 10 for silver chloride, 10 minus 13. So what's going to happen is, as I add the silver, I'm going to precipitate out the bromide first. Until I saturate it with respect to chloride. And so I have to calculate. It turns out, if I try to separate bromide from chloride, this turns out to be an unsuccessful fractional precipitation, because once I hit chloride, I've only precipitated out, let's say, 80+% bromide out of this. I've done the calculation before, but you can't see. It looks like it'll work. There's a difference there. What about if I tried to separate chloride from iodide? That would work for sure. Because if you look at silver chloride, it's 1.8 times 10 to the minus 10. If you look at silver iodide, it's 10 to the minus 17. That's 7 orders of magnitude difference. So what's going to happen is, as I add the silver iodide precipitates first because it's a lot less soluble. And they split the same way. Eventually, I'm going to add more and more silver until I get to a point where silver chloride is just about to precipitate. And then I do these two calculations. I calculate the concentration of iodide remaining and then the percent precipitation. And in this case, it's going to be like 99.9999% precipitated. Very little iodide left. And so that would be an effective way of separating out these. Now, two things that make this problem more complicated. One thing are the initial concentrations. Here I expect the iodide to precipitate before the chloride based on the KSPs, but the KSPs also rely on the concentration over here. If I have lots of iodide, the same thing's going to happen. Iodide's going to precipitate first, but if I have lots of chloride, that could change it. Because if I have lots of chloride, that's common ion, and that'll make it less soluble. And so the initial concentrations will play a role. In the last example that we just did, which was the separating out calcium and barium, both of these had the same initial concentration. But let's say the barium were, 1,000 times more concentrated. If the barium were 1,000 times more concentrated, then we wouldn't need as much hydroxide to precipitate out.
So is that saying like as you increase the concentration of hydroxide, the concentration of the calcium decreases, and that's what's causing the precipitation?
Mm-hmm. It would be like the common ion effect. The solubility is related to the calcium concentration, the barium concentration. Solubility goes down. It's common ion. The other thing that influences is how it splits apart into ions. Does it split up into 2 ions, 3 ions, 4 ions? In this case, both split up into the same, 2 ions. There's not 2, 3 ions. And so it's a fair comparison to the KSPs, but when we have situations like in the book they're trying to separate iodide. They're trying to separate silver and lead using iodide. And so if we look at silver and lead iodide, here. Lead iodide here is 10 to the minus 9. Silver iodide is 10 to the minus 17. So 10 to the minus 9 versus 10 to the minus 17, easy separation, I think, because huge difference in solubility. However, silver iodide breaks up into 2 ions, so the solubility is the square root of this. Square root of this would be 17 divided by 2, which would be about 8. You know, 8, 10 to the minus 8 solubility.
Can we do another example? I think I'm getting it. I'm not sure.
Okay. However, if we look at lead iodide, it's 10 to the minus 9, but it's the cube root. And so that would be 10 to the minus 9 divided by 3 would be 10 to the minus 3 solubility. I mean, I think it still works. All right, we could do another example of fractional precipitation. What do you want to separate? Which 2 ions in a mixture would you want to separate? It could be cations or anions. Well, we separated cations here. Maybe we'll try to separate anions. Okay, give me 2 anions that you think you might try to separate. Anybody have 2? Just pick 2 anions that you want to try to separate from each other. Let's see if you can do it successfully. Nitrite. All right, and so nitrite's 1, and then what would be another anion? Nitrite and sulfide. I'm going to try those 2. It looks like it should be pretty successful because nitrite is 10 to the minus 4 and sulfite is 10 to the minus 14. But there's a trick to this, and that's how they split up. This one splits up into 2. So the solubility would be like around 10 to the minus 2. This one splits up into 3. Splits up into 3, the solubility would be 1/3 this, which is going to be about 5, 4, 5. You know? So it still seems okay. We should still be able to separate nitrite and sulfide. Although nitrite and sulfide aren't that common. So do you want to do nitrite and sulfide, or do you want to do something else more common?
More common, I'm still trying to understand it right now. I don't want anything to.
All right, let's try to separate bromide and iodide. Let's say I have a mixture of bromide and iodide, and I want to separate one from the other. So those are pretty common. Or chloride and iodide. Maybe let's do chloride and iodide. That would probably work pretty well. And so let's say I had some iodide in here and some chloride in here. I want to separate one from the other. There's going to be cations in here, most likely sodium, because sodiums are salts are all soluble. And so I want to separate the iodide from the chloride or the chloride from the iodide. Now, the first thing is I have to look for a cation that has a difference in solubility for chloride and iodide. So one cation I could use is silver. If I use silver iodide is 10 to the minus 17, whereas silver chloride is 10 to the minus 10. There's a pretty big difference there. Are there any others that I could use? So I'm looking for chlorides. Mercury is another one. I could try to use mercury 1 ions. Mercury 1 chloride is 10 to the minus 18. Mercury 1 bromide is 10 to the minus 23. They both split the same. If they both split the same, then I'm going to precipitate mercury 1 bromide first. It's a lot less soluble, and then saturate it here and stop. For silver, silver iodide would precipitate first, and then I'd stop right before silver chloride begins to precipitate. Lead, you can try lead as well. Lead 2 iodide is 10 to the minus 9. And lead 2 chloride is 10 to the minus 5. 10 to the minus 9 and 10 to the minus 5. It's 4 orders of magnitude. No, chloride and iodide. We're looking at different cations. So one potential cation is silver.
Right.
Another potential cation is lead, and another one is mercury.
What kind of like they do, or maybe some split or something?
No, we're looking for something that gives us differences in solubility. So for example, here, we look at silver bromide, it's 10 to the minus 13, silver chloride is 10 to the minus 10. Or actually, we're doing chloride and iodide, sorry. So chloride's 10 to the minus 10, and
So how much of a difference?
the bigger the difference, the better.
Okay.
Yeah. And so which one has the biggest difference so far? Yeah, 10 to the minus 17, 10 to the minus 6, 10 to the minus 10. That's 7 orders of magnitude difference. Versus mercury. Mercury iodide. 10 to the minus, actually, mercury might be it. So mercury could be very effective at separating these. So mercury, I think, would work pretty well. Lead maybe not as good because it's only 4 orders of magnitude, so lead might not be effective. Which one do you want to try, mercury, lead, or silver?
Mercury.
Do mercury? Okay. This one should work pretty well.
Did you get the sodium from this? I mean, the cap sodium.
No, it doesn't have to be sodium. It could have been potassium, just some soluble. So instead of sodium, I just pick sodium, but any group 1 or ammonium,
Oh, okay.
iodide or chloride would work here. So what I do is just dissolve it in water. Now, to make things easier, I'm going to put the concentrations the same, 0.100 molar iodide, 0.100 molar chloride. But if the concentrations were lopsided, that's going to change things. Right now, which one do we predict to precipitate first? Right now, the one we predict to precipitate first is the iodide, because, yeah, 10 to the minus 29, but the situation is, what if I have lots and lots of chloride? If I have lots and lots of chloride, that's going to change the amount, because the first calculation we do is this. The first calculation we do is we calculate the concentration of mercury required for precipitation. We do not calculate the solubility. We don't bother calculating the solubility. In fact, calculating the solubility is a waste of time because it just ends up confusing people. The concentration doesn't just depend on the KSP. And so we're looking at precipitation for, let's look at the iodide here. And so what we're looking at mercury 1 iodide, Hg2I2. Hg2I2 solid. Hg2I2 solid forms Hg2 2+. This is diatomic cation plus 2 iodine. And so the KSP is equal to the Hg2 2+ concentration times the iodide concentration squared. So I'm interested in how much mercury I need to add to saturate it and precipitate it. And so the concentration of the mercury that's required to precipitate iodide is equal to the KSP divided by the iodide squared. And this is just to saturate it. In order to precipitate, I need to go above it, right? And then we'll precipitate. that concentration? That concentration is, well, the KSP for mercury 1 iodide is 4.5 times 10 to the minus 29. Divided by the iodide concentration squared. So 4.5 times 10 to the minus 29 divided by 0.1 squared. 4.5 times 10 to the minus 27. Now, if I change this, so for example, let's say I have lots of iodide. If I make the iodide 10 times more concentrated, then that means I need less mercury. I need 100 times less mercury. What about chloride? So we're going to have the same equation. Hg2Cl2 solid is going to go to Hg2 2 plus 2 chloride. And so when we look at the KSP for this, the KSP for this is going to be equal to Hg2 2 plus times the chloride concentration squared. And therefore the Hg2 2 plus concentration is going to equal the KSP divided by the chloride concentration squared. The KSP for mercury 1 chloride is 1.3 times 10 to the minus 18. This is equal to 1.3 times 10 to the minus 18 divided by 0.1 squared, 0.100 squared. So 1.3 times 10 to the minus 18 divided by 0.1 squared. 1.3 times 10 to the 16. So which one's going to precipitate first? This one. However, what if I had lots and lots of chloride? Well, even if I had, let's say I had 1 billion times more chloride. If I had 10 billion times more chloride, then actually no, it's squared. All right, so maybe if I had like 1,000, 10,000 times more chloride than iodide, then the chloride might precipitate first. You know, because which one precipitates first depends on both the KSP and the concentration that's given. And so this one precipitates first. In fact, it's gonna be difficult. Because 10 to the minus 16 molar is barely anything. So as soon as I add a tiny bit of mercury, both precipitate. But if I'm very, very careful, I can get just the iodide to precipitate first. And so what I'll do is we'll just slowly add mercury 1 on after that.
So based on, so we calculate the concentration required, the concentration of mercury required to precipitate out both ions.
Yeah, and then see which one precipitates first.
And then from there, we're basically just solving just.
Yeah.
So since the mercury 1 iodide, since we found that one precipitates first, that's where we're starting from now.
Yeah.
Okay.
So what we do is we figure out, this one's precipitating out first, and we need to stop here. Otherwise, both precipitate.
So, I don't know which one precipitates first.
The one that requires less. This one only requires 10 minus 27 moles per liter. This one requires more, 10 minus 16. So we start off with 0 mercury, and then we increase it. This one's going to be very difficult to do because the concentrations are so small. But in theory, we can increase the concentration of mercury. When the concentration of mercury 1 hits or becomes greater than 4.5 times 10 minus 27 molar, then mercury 1 iodide precipitates. Mercury 1 iodide begins to precipitate. Then we keep increasing the mercury. We keep increasing the mercury until we hit a mercury concentration of 1.3 times 10 minus 16. Once we hit that concentration, then we have to stop. Otherwise, the chloride begins to precipitate. And so this is the max. Mercury 2, mercury 1 we can add is Hg2, 2 plus. We need to stop here because if we keep adding mercury 1, both precipitate, and we don't want both to precipitate. And so the question is, how much iodide remains at this point? And so we calculate the iodide remaining at this concentration. So the iodide that's remaining at this concentration is equal to the KSP divided by the mercury concentration, and then we need to take the square root of that. And so the mercury concentration is going to be 1.3 times 10 minus 16. And so we'll take the KSP for the mercury iodide, 4.5 times 10 minus 29. 4.5 times 10 minus 29 divided by 0. Well, actually, I'm not going to write that in decimal form. I'll just write it in civic notation. 1.3 times 10 minus 16. So 4.5 times 10 minus 29 divided by 1.3 times 10 minus 16. Cool. And then we need to take the square root of that. We get 5.8835 times 10 to the minus 7 molar. So there's going to be some iodide remaining. The amount of iodide that's remaining will be 5.8835 times 10 to the minus 7 moles per liter. So once we get the iodide concentration that's remaining, we're going to calculate the percent iodide remaining. The percent iodide that remains is equal to 5.8835 times 10 to the minus 7 molar that we have versus the original 0.100 times 100%. And so we'll take this is the amount I have left over, 10 to the minus 7. The original amount I had in there was 10 to the minus 1, or 21 times 100. And that's going to give me 5.8835 times 10 to the minus 4% remaining. Okay, if that's the percent remaining, then I want to calculate the percent precipitated, so it would be 100% minus that. So the percent precipitation is equal to 100% minus the percent remaining. (99.999% precipitation). So the iodide, I had 99.999% of the iodide precipitate before the chloride begins to precipitate. And therefore, this is a very effective fractional precipitation. Now, if the KSP values are very close to one another, then it's going to be difficult. And so, for example, lead, it might not be a good separation with using lead. And the reason I suspect it might not be a very good separation using lead is because, lead 2 chloride is 10 to the minus 5, the KSP. And then lead 2 iodide is 10 to the minus 9. So it's not going to be as effective because there's only 4 orders of magnitude versus what we had. We had a lot more with the mercury. With the mercury, we had 9, what is that, 9? 11 orders of magnitude, 11 orders of magnitude difference. So this is the type of calculation we have to do. No, we didn't calculate the solubility. There's no need to know the solubility. What we calculated is what did we calculate? The concentration required for precipitation. The concentration of the precipitating agent required for precipitation.
And that's just to precipitate out the iodide.
Yeah, that's to figure out which one precipitates first and where to stop. That's why we need that. We've got to do 2 calculations.
So if we were to do this, if we were to look at this in like a stepwise type of thing, so the first step would be to figure out which will precipitate first.
Yes.
And then the second step would be to calculate the concentration remaining, percentage,
Yeah.
and the percentage of precipitation.
Right.
Okay.
So this one's for cation, right? Do you have to do something similar for cation?
Yeah, well, we did it for the barium from calcium.
Can we do another example on that?
Of cations?
Yes.
Pick 2 cations that you want to separate. Two cations in this list.
Iron and lead.
Okay, let's try to separate iron from lead. Iron 3 or iron 2?
3.
Okay, we'll try to separate iron 3 from lead 2. So if we look at iron 3, we have choices. We have arsenate, we have ferrocyanide, which is hexacyanoferrate. We have hydroxide, we have phosphate. When we look at lead, we see if we have any of those. Actually, we do. We could try using hydroxide. If we look at lead 2 hydroxide, it's 1.2 times 10 minus 15. Let's look at iron 3 hydroxide. Iron 3 hydroxide is 4 times 10 minus 38. That should work very well. It's a huge difference in the case. But they split up differently, so it could be deceptive. We already did hydroxide. Let's pick another anion instead. Hydroxide. Do we have maybe phosphate? Let's see if we, iron 3 phosphate is 1.3 times 10 minus 22. lead 2 phosphate. Fortunately, we don't have lead 2 phosphate. Let's look at carbonate. We don't have iron 3 carbonate. So it looks like we're stuck with hydroxide. But hydroxide should work very well. So this is going to be a mixture of lead 2 plus and iron 3 plus. Now the initial concentrations will have an impact. And so to keep things simple, I'm going to keep it 0.100 molar lead 2 plus and try to separate it from 0.100 molar iron 3 plus. If these are very lopsided, it's going to change the amount required. Okay, what's the first calculation we need to do?
We have to see which one will precipitate first.
Yeah, and what's the calculation we do for that?
We'll do, we'll take the, lead 2. Lead 2 hydroxide, right?
Yeah.
So we'll just start with the iron 2 hydroxide. So it's gonna separate out into iron 2 plus.
So we're doing iron 3.
Oh, iron 3. Oh, my bad. Oh, cool. So yeah, it's separate into iron 3 plus, and then plus 3 hydroxides.
Yeah.
And then the KSP for that would be the concentration of iron 3 plus, and then multiplied by the concentration of hydroxide raised to the third power.
Yeah. All right, then what are we calculating here?
We're calculating the concentration of hydroxide.
Yes.
And so that's going to be
This is the hydroxide required for precipitation.
yeah,
Is equal to,
the KSP divided by the concentration of iron, but that has to be cube rooted, right?
yeah. All right, so let's go ahead. The KSP for iron 3 hydroxide is 4 times 10 to the negative 38. Divided by the iron concentration, which was given as 0.1. And then take the cube root of that. $7.3681 times 10 to the negative 13. What did what come from? Oh, the cube root. We're solving for hydroxide. It's equal to KSP divided by that. But I'm not solving for hydroxide cube, I'm just solving for hydroxide, so we have to take the cube root of both sides. Okay.
Did you have on the KSP was raised to the third power? The FE3 plus times the OH negative raised to the third?
Yeah.
So you would want to find just the concentration required for the precipitation with respect to the hydroxide. We need to cube root the entire equation on the right hand side because we're just looking for one hydroxide. Okay. All right. Okay.
Okay, so you got it? Yeah. Okay. All right, next one. Next, what we got to do
two hydroxides. And the NSP is going to be the concentration of Pb2 plus, Y2 plus, and then hydroxide squared. The concentration of hydroxide.
The concentration of hydroxide required for precipitation has to be greater than. All right, and so here it's going to equal what?
That would be the KSP divided by the concentration of Y2 plus, and then square root.
Square root. So,
What was the KSP for the top one? For the iron blue hydroxide?
the KSP for iron 3 hydroxide. Put that here. 4 times 10 to the negative 38. And the KSP for lead 2 hydroxide is 1.2 times 10 to the negative 15. This will be 1.2 times 10 to the negative 15 divided by 0.100 and then the square root. So 1.2 times 10 to the negative 15 divided by 0.1. Take the square root of that answer. This comes out to 1.0954 times 10 to the negative 7 molar. So which one precipitates first? Yeah. Because it requires a much lower concentration, so this precipitates first. And where do we stop? Yeah, we stop here. So we keep adding until the concentration hits this point, and then we stop. And so what's the next calculation? The next calculation is to calculate the concentration of iron 3 remaining at the stopping point. So the concentration of iron 3 remaining at the stopping point is equal to what? Tell me.
The concentration of the stopping point is going to be equal to.
Okay, what is the concentration we're calculating?
Is it the concentration of iron?
And what is it equal?
That's the KSP divided by heavy hydroxide.
Yeah.
Would that be raised to the third power?
Yeah. So this is remaining at the stopping point. And so this was 4 times 10 to the minus 28, to recall, over the hydroxide. The KSP we got off the table. What's the hydroxide?
What was that? Oh, was that 1.8?
It's 10 to the minus 38. Is it 0.100 at the stopping point?
Oh, no, it's 1.095.
Yeah, that's a very common error. People write 0.100 here. It's not 0.100. It's the concentration of hydroxide at the stopping point. 1.0954 times 10 to the minus 7 cubed. It's 10 to the minus 38. So I got 4 times 10 to the minus 38 divided by 1.0954 times 10 to the minus 7 squared. So 3.3336 times 10 to the minus 24 molar. Okay, what do we calculate next? Yes, we're going to calculate the percent remaining. What is it?
Yeah, 100%. The percent remaining of the iron 3 plus, which is equal to 100% minus the remaining.
No, that's not it.
Oh, it's the remaining divided by the, yeah, it's the remaining divided by the original concentration.
Yeah, so it's the remaining 3.3336 times 10 to the minus 24
Divided by the 0.100
divided by the 0.100.
times 20%.
Yeah, times 100%.
That's what I think.
So this is going to be divided by 0.1 times 100. I get 3.3336 times 10 to the minus 21% remaining. Okay, now we want to do the percent what?
Percent of the iron 3 plus that was precipitate.
Yes. Right. And so the percent iron 3 plus precipitated is equal to what?
That's the 100%.
Yeah, that would be 100% minus this.
Yeah.
I don't know if your calculator can handle it. Mine can't. There are too many nines. It's going to be 99.999. How many nines are there? They're going to be 20 nines after the decimal. And you know, your calculator is going to round it to 100% precipitation. Do you see that? Because your calculator can't carry that many decimal places. You get 100%?
Yeah.
There's some little left. All right, so this would be a very effective separation. We could very effectively separate lead from iron 3 by using hydroxide. We would get practically all the iron out and then just leave the lead in solution. Okay, is that good? Okay. All right. So let's look at the next series of topics. The next series of topics is manipulating solubility. We could either decrease or increase solubility. That is, we can precipitate or dissolve things. So, for example, decreasing solubility. What are ways to decrease the solubility of something? One way usually is to decrease the temperature. By decreasing temperature, are there other ways to decrease the solubility? Another way of decreasing solubility is the common ion effect. So decreasing common ion. Common ion is your precipitating agent. Like in the last example, the common ion would be hydroxide. The more hydroxide you add, the less soluble things become, especially for the iron. Sometimes pH can play a role in this as well. So making it more acidic or make more basic can have an impact on solubility. How about if we want to increase the solubility? What are some common ways to increase the solubility? One common way is increasing temperature. You can get it to dissolve more. The other way is removing, well, we'll go to pH And the other way is removing common ion. The way we can remove common ion is by either complexing it or some other reaction. To remove. Okay.
On that side.
This basically
Yeah.
decrease the temperature. This is decreasing solubility, increase common ion, and then pH.
Does that say complete or complexity?
Complexing or some other reaction. So we'll look at the pH, for example, here. Is it okay to get rid of this?
Yeah.
So we might get a question like this: at what hydroxide ion concentration will 0.100 molar magnesium nitrate precipitate? So this is like a fractional precipitation, but we only have one species. And we want to know what the concentration will be here. And so we know that the KSP is equal to the magnesium concentration times the hydroxide ion concentration squared. And so the hydroxide, this is the hydroxide concentration required for precipitation. It's just equal to the KSP divided by the magnesium ion concentration. And then we'll take the square root of that. So the KSP for magnesium hydroxide, we can just get from the table here. Magnesium hydroxide is 1.8 times 10 minus 11. 1.8 times 10 minus 11 divided by the magnesium concentration, which is given as 0.100 molar. And we'll take the square root of that. So 1.8 times 10 to the minus 11 divided by 0.1, answer, and then square root of that answer. Well, 1.3416 and 10 minus 5. That's the saturated. What we need to do is we need to supersaturate it. And so the hydroxide needs to be greater than this in order for precipitation to occur. If it just equals that, then it's just saturated. And so we need a concentration greater than that. Well, what this means is this is the concentration of the hydroxide. So we can get POH. POH is going to equal the negative log of this concentration here. And so I'll just take the log of the last answer. 4.8724. 4.8724. Which means that the pH must be equal to 9.1276. 9.1276. So what does this mean? This means if I hit this pH, then it's just saturated. What I need is more hydroxide. So more hydroxide is a higher pH or a lower pH? Higher pH. And so what I need is a pH higher than this in order to precipitate it. So if I have pH 7, I'm not going to get any precipitate because I don't have enough hydroxide. If I have pH 8, will I get a precipitate? No, I'm not going to get a precipitate at pH 8. If I hit pH 9, will I get a precipitate? No, I have to hit a pH greater than 9.13. And so the pH needs to be greater than 9.13 in order for precipitation to occur. I just go too soon. And so this will result in precipitation. Anything lower than this, I'm not going to get precipitation. And the higher I go, the more I'm going to precipitate because the more hydroxide I add, the less magnesium I'll have. Here, there's no stopping point. I can just keep going and keep going and keep going, right? Because I don't have to worry about a second cation precipitating. But normally where we stop is like 99.9. If we stop at 99.9%, that's considered complete, an arbitrary definition for complete precipitation. And so this is how pH can influence it, higher pH and lower pH, that kind of stuff. Some things aren't so easy. So for example, let's look at something like magnesium chloride. Magnesium chloride, what's the pH required for precipitation on that? Well, that one's a bit more tricky. Magnesium chloride goes to magnesium ion and 2 fluoride ions. Well, the situation about magnesium is magnesium neutral, but fluoride is not neutral. Fluoride is a weak base. Well, if fluoride's a weak base, then weak bases hydrolyze water, right? And we end up with some kind of POH and pH. But in this case, what we do is we do special treatment for this. This is called combined method. And so this is KSPA. It's KSP combined with acid. So this is a combined method of multiple equilibria. When we have multiple equilibria, we have the stepwise method and the simultaneous method. This is the third method that only works under certain scenarios. The certain scenarios that it works is equation 1. So we're going to call equation 1. Equation 1 has to have a small k. It's got to have a small k value. 3.7 times 10 minus 8. That's pretty small. What that means is we don't generate that many ions. It's not very small. Then what we do is we attack it with acid. So equation 2 is if I have acid, H plus or H3O plus, what does it react with? Well, the acid is going to react with the strongest base present. What's the strongest base present here? It's either fluoride or water. Magnesium ion is neutral. So it's going to attack the fluoride, the strongest base present. And so I'm going to have acid, which in this case will just be hydronium. And I have 2 fluorides, so I'll need 2 hydroniums to react with 2 fluorides. And I'm going to make 2 HF plus 2 honors. The second part of this is the K in equation 2 has to be very large. And so for the combined method to work, this one has to be very small, and this one has to be very large. And then it should work. Well, this should be very, very large because it's strong acid H3O plus weak base. That should be very, very large, but we need a number for this. In order to get the number for this, you reverse this equation. If we reverse this equation, do you recognize it? If we reverse it, it's HF plus water yields hydronium plus fluoride. What does that sound like? Well, HF is a weak acid, yeah. But what type of equation is that? Acid plus water yields hydronium and conjugate base.
Oh, conjugate base. Oh, is that the Henderson-Hasselbalch?
Well, kind of. It's Henderson-Hasselbalch is either based on the Ka equation or the Kb equation. What this is the K for this is equal to 1 over Ka for HF. But it's doubled because it's 2 HFs rather than 1 HF, so we got to square it. So what we can do is we can combine equation 1 and equation 2. If we combine equation 1 and equation 2, we get MgF2 plus 2 hydroniums. Fluorides cancel. This is going to yield magnesium 2 plus 2 HF plus 2 waters. This is the K for the combined. K for the combined is equal to KSP divided by Ka squared for HF. So KSP is 3.7 times 10 to the negative 8. And then Ka for HF is 6.6 times 10 minus 4. Squared. And so what is KSPA for this? So it's 3.7 times 10 to the negative 8 divided by 6.6 times 10 to the negative 4 squared. Is that what you guys got? Let me try it again. You got it? Okay. All right, we'll go with that. So what type of question would you be asked for something like this? The type of question that you'd be asked for something like this is, what is the solubility at pH? Well, I'm going to keep it simple. What is the solubility in a pH 4.00 buffer? The reason I'm doing it this way is because pH is going to give us the hydronium ion concentration. Now, the hydronium ion concentration could either be the initial hydronium or the equilibrium hydronium. Are we out? Okay, we're out of time. So we'll finish this problem next time. Which one? This one? This one? This one?
Yeah, it's supposed to be fluoride.
Oh, yeah, sorry. It's fluoride. Okay, I'll see you tomorrow. We have a kinetics lab, which is, I haven't gotten to kinetics, so we'll go through the procedure in the lab. I'll post something, but I'm gonna change the procedure a little bit from what I post.
Should we prep our notebooks? Or-
You don't have to prep your notebooks.